Assalamualaikum and good day. Today I will be presenting my project titled Architectural Overview of the Apple M1 Processor with a focus on the instruction cycle in ARM architecture. This presentation will explain how instructions are processed in the Apple M1 and why its architecture is important in modern computing. The instruction cycle is one of the most important concepts in computer architecture and computer organization. It describes how a processor reads, understands, and executes instructions stored in memory. Every action performed by a computer, such as opening applications, browsing the internet, or displaying graphics, depends on the continuous repetition of this instruction cycle. In older processors, instructions were executed one at a time in a simple sequence. However, in modern processors like the Apple M1, the instruction cycle is much more advanced. The M1 uses techniques such as pipelining, parallel execution, branch prediction, speculation, and out-of-order execution. These methods allow the processor to execute billions of instructions per second while still maintaining low power consumption. The Apple M1 processor was introduced on 10 November 2020 and is based on the ARM architecture. This marked a major transition for Apple from traditional x86 processors to ARM-based designs. Instead of completing one instruction before starting another, the M1 allows multiple instructions to exist at different execution stages at the same time. Understanding its instruction cycle helps us understand how high performance and energy efficiency are achieved together. ARM processors follow the Reduced Instruction Set Computing or RISC philosophy. RISC focuses on simple, fixed-length instructions that can be executed quickly. This design makes decoding easier and allows efficient pipelining. In general, the ARM instruction cycle consists of 6 main stages. First one is instruction fetch, instruction decode, instruction issue and dispatch, execution, memory access, and finally, write back. Unlike older processors, ARM-based processors such as the M1 can overlap these stages to improve performance. The instruction cycle begins with the instruction fetch stage. This process starts with the program counter or PC, which stores the address of the next instruction. Using this address, the processor fetches the instruction from the L1 instruction cache, which is much faster than main memory. If the instruction is not found, it is retrieved from the lower level cache or from RAM. Once fetched, the instruction is pre-decoded and the program counter is updated to the next instruction address. After fetching, instructions move to the decode stage. Here, the processor identifies what type of operation is required, such as arithmetic, logic, or memory access. Because ARM instructions are fixed in length, decoding becomes simpler and faster. The Apple M1 uses a wide decode architecture, allowing multiple instructions to be decoded in a single clock cycle. Decoded instructions are converted into micro-operations and then dispatched to suitable execution units. The execution stage is where actual computation takes place. The Apple M1 contains multiple high-performance and efficiency cores enabling parallel execution. Arithmetic operations are handled by ALUs, floating point operations by FPUs, and vector units support multimedia and machine learning tasks. The M1 uses out-of-order execution, meaning instructions are executed as soon as their required data is available, rather than strictly following program order. This improves pipeline efficiency and reduces idle time. Memory access occurs when instructions need to read or write data. Unlike traditional systems, the Apple M1 uses a unified memory architecture where the CPU, GPU, and neural engine share the same memory. This design reduces data duplication, improves communication between components, and lowers memory latency. Dedicated load and store queues also allow memory operations to be handled efficiently without stalling the pipeline. In the write-back stage, the results of executed instructions are stored into registers. Although instructions may execute out of order, the Apple M1 uses a reorder buffer to ensure results are committed in the correct program order. This maintains correctness while still benefiting from parallel and speculative execution. Efficient register management allows faster access to results and improved instruction throughput. Pipelining allows multiple instructions to be processed at different stages at the same time. While one instruction is executing, others may be decoding or being fetched. The Apple M1 uses deep pipelines to maintain continuous instruction flow without relying on a very high clock speeds. Pipeline hazards are handled using instruction reordering, branch prediction, and speculative execution. In conclusion, this project has examined the architecture and instruction cycle of the Apple M1 processor. The M1 demonstrates how modern processors improve performance not by increasing clock speed, but through efficient design, parallel execution, intelligent scheduling, and unified memory architecture. Overall, the Apple M1 serves as a strong example of how ARM-based processors are shaping the future of computing through balanced performance, energy efficiency, and system integration. Thank you for listening.